All right, guys, you should have just watched the video on how a computer works, binary and data. So hopefully you've got a little bit of an idea how computers think or appear to think. Okay. On my screen here, I've got some images of a power switch, which you notice it has a 0 and a 1 on it. A lot of them do these days. You might not have realized it, but that's kind of how computers think. They see the 0, which on this switch is the off location, which means that circuit is not closed and no electricity is flowing through it. So it's the off position or the dark position. And then you've got the 1 side, which is the on position, which means that circuit is closed and electricity is flowing through it. You know, the device is working. That's how you turn it on. But computers think in terms of little tiny circuits that are either closed or open, meaning they're either on or off. They're either electricity is flowing through it or there's no electricity flowing through it. So that's kind of how computers appear to be thinking. Really, all they're doing is evaluating electrical circuits and whether they're turned on or off. And with different combinations of on or off, we can get different outputs, different results that as humans we can understand. But computers, all they know is 0 and 1. They're actually really dumb. They just know, is this on or off, 0 or 1. So in the video, they were talking about an 8-bit binary system. So they go up higher than 8 bits. I mean, this 8 bits is where we're going to start. We can count up to a certain limit, which happens to be 255 would be the limit that you can count up to with an 8-bit binary. And where that 255 is coming from is if I had one of each of these numbers here, if I added 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1, 255 would be the sum. Okay, so which means that the highest number I could count to with just the 8 bits would be 255. So if all these zeros here were turned into ones, and I'm including all those, so the number 11111111 would be 255 in binary. That sounds confusing, I know, but hopefully by the time you're done seeing this, it'll make more sense. So let's start down here at the bottom of our numbering system, our human numbering system. I'll just kind of show you how the binary counts here. Okay, so the number 1, there happens to be a number 1 here. So if I turn on the number 1 by putting a 1 there, this one is on, and all of these other ones are off. Okay, if it's on, I count it. If they're off, I don't count it. Okay, so the only one that's turned on is a 1. So my number right there represented in binary is 1. So 1 in binary is actually 1. A lot of zeros in front of it, but 1 is 1. 2, reset that. The number 2 in binary, I would turn on the 2 placeholder. Okay, and that gives me the number 10. So the number 10 in binary is actually, to humans, number 2. When you're reading binary, you don't have to read all these leading zeros here. As long as you're getting the binary, your first one, you want to read your first one on. Make sure you read that entire digit. But that number right there, 000010, I just ignore the front zeros and just call it 10. That's the number 2. Okay. Number 3, it would be one of these and one of those. So everything else is turned off. The only ones that are turned on, the 2 and the 1, you add those together, you get the number 3. So 11 in binary is actually our number 3. I'm going to do a think aloud here as I work through figuring out what the binary equivalent of just some random number is, up to 255. So you can kind of understand how the thought process works when you're trying to determine what number a binary represents. Okay, so let's go with the number 33. Okay, 33 is the number I'm shooting for here. And I don't want to waste all my time working from the back side. I'm going to work from the biggest number I can. So I know that 32 right there will fit into 33 at least once. Okay, so if I include in my number 1 instance of 32, I'm going for 33. I just need to add 1 more. I can come way down here on the end and just turn on the 1. Oops, turn on the 1. And I've got 32 plus 1 is 33. So the number 33 in binary would be 100001. Okay. A tougher one. Let's go 117. It might be helpful to you if you get a piece of sticky note or a piece of paper and just kind of write this down, because it's very, very simple math. It's just addition and subtraction. But to kind of keep your place, maybe just jot that number down. So I'm going for 117. So out of these 8 numbers here, the biggest number that I can fit into 117 without going over would be 64. So I'm going to go ahead and turn one of those on. Okay, so I've got a 64 in there. So if I take 64 from my original 117, what do I have? And if you need to do this too, you come down here and you open up a calculator. 117 117 minus the 64 that I've already got, I'm left with 53. Okay, so what's the next number that will fit into 53? Like I can also fit a 32 in there. Okay, so if I turn the 32 on, I've got 64 plus 32. That would be 96. 96 is my number running total. I'm going for 117. So if I subtract that out there, 117 minus the 96, I'm shooting for another 21. Okay, going back down the numbers here, 16 will still fit into 21. So I'm going to go ahead and turn one of those on as well. Okay, so now my number is 64 plus 32 plus 16. Which leaves me 5. So if I subtract out the 16 from the 21, it leaves me 5 to go. Okay. Next number in line here is an 8. Well, 8's too big. 8 won't fit into 5, so I leave that one turned off. I leave that as 0. Okay. Next smallest number is a 4. 4 will go into 5 once, so I can turn on a 4. I'm putting a 1 there in that placeholder. The running total here, I had 5 minus the 4. Leaves me with just one more to go. So I know I can skip the 2. 2 is going to be too big to fit into that 1, but there's the 1 I need right there. So if I turn on the 1 right there, and I go back through and I add up all the numbers that I have 1s over, 64 plus 32 plus 16 plus 4 plus 1 is 117. So the number 117 in binary would be 1110101. I know it sounds kind of tedious, but that's how computers think. Like I said, they're really dumb. All they know is zeros and ones. So if we want to communicate something to a computer, if we want to communicate the number 117, we input 117 on our keyboard there. But what the computer sees is that weird looking number right there, just a bunch of zeros and ones, and it understands what we're talking about. So I want to show you this link that I've got on the Classroom stream there. A couple of links I want you to use to kind of practice and get a little bit more used to binary code. When we do a quiz over this, we'll have a few questions on there that'll be binary, where I'll show you some binary and ask you to tell what number it represents. So one of the links I have on the Classroom stream is a text to binary code converter. And I put this on there just so that you could see that we can actually do letters in words in addition to numbers and stuff. If I type in my name, up here, down here, it gives me the binary equivalent of the letters JAMES. So that would be my name in binary. If I type in just one letter up there, I can kind of see what one letter looks like. That binary number right there is the letter A. So if I type a letter A on keyboard right there, even though I know what A is, when it goes into the computer as input, it sees this binary number down here. It doesn't have any idea what A is, but that number, once I hit the letter A, it sees that number there, and that number would be programmed to put an A up on the screen. So it makes sense to me, the human being, using the computer. You could probably type out some like secret messages to your friends using this. You can see that they would get very, very long, and they'd be a little bit harder to decipher, but it's possible to write messages to your friends with binary code and see if they can figure it out. If they've got a converter like this, it wouldn't be too bad. The other link that I've got on the Classroom stream is for the binary game. Okay, so the binary game works like this. When you start the game, it's going to show you your placeholders here. with the 128 through the 1, so the binary placeholders here. And then it's going to give you two types of questions. One is it's going to show you ones and zeros and ask you to type in the number that it represents over here. The other type of question is it's going to give you a number here, and it wants you to actually turn on the numbers that are going to make it equal. So 8 and 2. Let me start it over. It got a little bit ahead of me there while I was talking. So let me start a fresh game here. All right, so it wants me to make the number 17. So some of these you can do pretty quick. I know that 16 plus 1 is 17. That was a pretty easy one. So once I complete that, when I get it correct, that block goes away, and more blocks keep coming up. So it's kind of like Tetris. If it gets all the way up to the top, my game's over. I just see what my score was. But if I complete an answer and correctly get it, it gets rid of that line of binary there. So as you're playing this here, like this one here is a different type of one where it's wanting to know what number is represented by 32 and 1. So I can type in, I know that's 33. If I get it correct, it goes away. It's wanting me to make a 15, which would be an 8, plus a 4 would be 12, plus 2 would be 14, plus 1 would be 15. 8 and 1 is 9. So as I'm going through this, it's just giving me both methods to try to help me practice reading and writing in binary code here. So I want you to play this a little bit. When we have a quiz over this at the end of the unit, there will be a few questions on the quiz that are going to be similar to this. I'll show you a binary number and ask you to tell me what actual number it represents, or I may give you an actual number and ask you to write the binary code equivalent of it.